So let's summarize. So what, and this is more or less the end of our discussion for justifying the fattest hyperplane. So, we have the general perceptron, the VC analysis, the sort of generalization analysis for the general perceptron. And what did we see there? The VC dimension is equal to D plus 1. So this links the in-sample error to the out-of-sample error, okay, for the general perceptron, which establishes the first step of learning, and that's fantastic. That's fantastic. Okay. It was great. Okay. And that's why the perceptron is such a good hypothesis set. But this is, dimension dependent. Okay, but that's still good. Okay. It links E into E out. Okay. Now, what are we analyzing? We're analyzing a particular algorithm, the maximum margin, the fattest hypothesis. So this general perceptron and this VC dimension and the corresponding link from E into E out applies for any algorithm, for any way of picking a perceptron that separates the data. Okay? Now we see that if you narrow your scope, if you focus on a very special way of picking the hypothesis, the final hypothesis must separate the data with maximum margin. It's the fattest separator. Okay, so the optimal, separator, hyperplane. Let's call this the SVM, support vector machine, although we haven't gotten there yet. Basically what it means is it's the fattest / max margin. Okay, now it's important to realize that it's still a hyperplane, so it's still a perceptron. It's just that the specific hyperplane separator is now chosen to be the fattest. Okay? And all kinds of other interesting properties emerged. Experimentally, we saw that bias, there's no reason for bias to go up. In fact, typically bias goes down a little bit, but variance, that thing goes down a lot. And that's because, the optimal separator is this maximum margin. It's sort of a well-defined, and it's not that variable hypothesis, even if the data varies a lot. So you change all this data a lot, and you don't change this at all. So there's no variance. Okay, you change the data a lot. On the other hand, PLA or something may change a lot depending on the data. Okay, so this means that E out, remember E out is equal to bias plus variance. And so that's going to go down. Okay, so there, experimental evidence that showed why the fattest is better. And that links to regularization and all that good stuff, all those good foundations we had before. Okay, but now, then we gave the argument that, the fat separators have, could have a lower VC dimension. So the VC dimension is at most, is at most, the min of D and the radius of the data. So how bounded is the data? Radius of the data squared over thickness plus 1. Okay. Now, in high dimensions, well, technically there's a dependence on D, but if you go into higher dimension and the data is tightly bounded, okay, and you separate with fat separators, then you could have a much lower VC dimension than the general case, than D plus 1. Okay. Now, just for full disclosure, let me mention that the hypothesis set with, fat separators is not well defined until you look at the data, because what hyperplane width should we put in here? Well, we have to look at the data, separate, and then look at the width. So in some sense, we're defining the thickness of our hypothesis set, i.e. our hypothesis set, but when we look at the data. So a little bit more work is needed to actually link this, into the theory that links E into E out. Okay, but we're not going to go through that. Well, you can see in the text, the proof that fat separators, cannot shatter as many data points as thin separators. Okay. Then there's another step to link that to E in versus E out, because to apply it, we need to know the thickness of the hypothesis set. But let's not get into those details. The point is that, fat separators have less separating power when the data is bounded. And you can get a link from E into E out, okay, that doesn't depend on the dimension. It just depends on how bounded is the data and how thick is the separator that you're using. Okay? And so again, it suggests that we might be able to go to high dimensions and control the out-of-sample error, providing that the in-sample error is small and the data is bounded, tightly bounded. Okay? And then we have this stunning result that the cross-validation error, E cross-validation, is at most the number of support vectors vectors divided by n. So if n is big and the number of support vectors is under control, the out-of-sample error is under control. And it looks like it's not explicitly dependent on the dimension. So again, another fantastic result that suggests we might be able to have a control on the out-of-sample error. That's all we care about, even in high dimensions. This says that we might have a link from E into E out, even in high dimensions, if the data is bounded. This says we can go directly and control the out-of-sample error if the number of support vectors is bounded. Now, so let me emphasize that this is the general perceptron, no matter how you pick the hypothesis. And these are the nice properties if you pick the hypothesis using this special property of going for the fattest. We had another algorithm which was picking a hypothesis from the perceptron hypothesis set, the hyperplane, which was the PLA. And it turns out that that's not so bad. It's not as bad as just pick as the most general case. It's possible to get a link between the cross-validation error and parameters that are not explicitly dimension dependent. So the cross-validation error for the perceptron learning algorithm is at most this guy R squared, the bound on the data, divided by n gamma squared. Where what is gamma? Gamma is the separation between the data. It is the width of the optimal separator, whatever it happens to be in. And the nice thing, so you do get a bound on the cross-validation. It's not quite as nice and clean as the optimal hyperplane. Okay, but there's another nice property that the optimal hyperplane delivers to us is that we know how to find it efficiently. Okay, so the algorithm. What is the algorithm? It's a quadratic program. So it's a bounded algorithm, n-cubed algorithm. On the other hand, the perceptron learning algorithm will find a separator, it has to end. So that was a miracle theorem that we proved, or you proved in the homework. It has to end, but we don't know when. It could go for a long time. In fact, the number of iterations is proportional to R squared over gamma squared. Okay, so that's the number of iterations for the perceptron learning algorithm. Okay, so let me summarize. We have studied the fattest separating hyperplane. We have an algorithm to find it, and it has all these nice properties, so we should use it. It self-regularizes, optimally regularizes, and we can link to E out, okay, in ways that are independent of the dimension. All right. So it's a nice, theoretically justifiable, algorithmically well-behaved. We have a nice algorithm. It's a very nice algorithm. The only thing that's wrong with our analysis up to now is we have focused on the separable case. And we know that data is typically not linearly separable. Okay? So we have to handle non-separable data. Question. Okay. So let's erase. And let's now talk about how do we deal with non-separable data.